The vast emptiness of space conceals celestial bodies of immense, untapped value. Among them, 16 Psyche, an asteroid belt object, presents a singular enigma. This metallic world, believed to be the exposed core of a protoplanet, orbits the Sun in silent solitude. Its surface, a vast repository of iron, nickel, and potentially platinum group metals, beckons future resource expeditions. Accessing Psyche, however, is not a trivial undertaking. Situated between Mars and Jupiter, its orbit necessitates advanced propulsion systems and precise trajectory calculations. The sheer scale of its metallic composition also demands novel extraction methodologies, far beyond conventional terrestrial mining techniques. Robotic exploration must precede any human endeavor to harness its riches. Reaching Psyche begins with orbital mechanics. Low-thrust electric propulsion, such as Hall-effect thrusters, offers the most efficient means to cover the immense distances. These systems utilize inert gases like xenon, ionized, and accelerated to generate a continuous, subtle thrust. The long transit times, spanning years, are a direct consequence of this energy-efficient approach. Upon arrival, detailed reconnaissance is paramount. Orbiting probes equipped with gamma-ray spectrometers, neutron detectors, and magnetometers will map Psyche's surface and subsurface composition. High-resolution imaging provides topographical data, identifying potential landing zones and areas of mineral concentration. This preliminary survey minimizes risks associated with direct physical contact. Landing on a low-gravity body like Psyche presents unique engineering challenges. Traditional landers are insufficient. Instead, specialized harpoons or adhesive anchors will secure robotic platforms to the asteroid's metallic surface. Maintaining a stable operational base in such an environment is critical for any long-duration mining operation, preventing unintentional orbital escape. Initial extraction efforts will likely involve robotic surface, samplers, and drills. These deployable units, equipped with laser ablation systems and mass spectrometers, can vaporize small sections of the asteroid and analyze the resulting plasma. This real-time compositional analysis refines the understanding of resource distribution across the asteroid. For larger-scale extraction, methods will adapt to Psyche's unique metallic regolith. Magnetic separation techniques could sieve valuable iron and nickel particles from less dense silicates if present. Alternatively, specialized cutting and grinding tools, resistant to the harsh vacuum and metallic abrasion, will pulverize surface material for subsequent processing. Powering these deep space operations requires robust, reliable sources. Solar arrays, though viable, diminish in efficiency further from the Sun. Compact fission reactors offer a more consistent energy output, critical for high-power mining equipment and life support systems, enabling continuous long-duration missions without reliance on solar flux. The raw material extracted from Psyche must undergo on-site processing. This involves refining the metallic ore to separate desired elements, such as nickel, cobalt, and precious metals, from the bulk iron. Technologies like pyrometallurgy, utilizing high temperatures or electrowinning, employing electrical currents in molten salts are candidates for this extraterrestrial refinement. Processing facilities on Psyche would be entirely autonomous, minimizing human exposure to hazardous conditions. Modular designs allow for expansion and repair using robotic fabricators. These structures must be hardened against micrometeoroid impacts and solar radiation, maintaining vacuum-sealed environments for high-temperature metallurgical processes. The refined metals will be stored in specialized containment units, designed to withstand the rigors of space travel. These containers prevent contamination and structural degradation during transit back to Earth orbit or to orbital construction facilities. Precise mass measurement and documentation are essential for inventory and payload management. Transporting vast quantities of material from Psyche presents its own logistical puzzle. High-capacity cargo vessels, potentially propelled by nuclear electric or solar electric engines, would undertake the multi-year journey. These ships operate on trajectories optimized for fuel efficiency rather than speed, ensuring maximum payload delivery. Unlike terrestrial mining, where waste products are often a local environmental concern, waste on Psyche must be managed in vacuum. Recyclable slag could be used as construction material for asteroid habitats or shielding, while truly inert waste might be safely deposited into stable heliocentric orbits or launched into trajectories away from populated zones. The economic viability of Psyche mining hinges on the value of its rare elements. Platinum group metals, critical for advanced electronics and catalytic converters, command high prices. A successful extraction program could significantly alter global markets, providing an abundant extraterrestrial source, reducing reliance on finite terrestrial deposits. A key difference from Earth mining is the absence of atmospheric erosion and seismic activity on Psyche. This stable geological environment allows for more predictable and systematic excavation plans. However, the lack of gravity necessitates active anchoring and propulsion for all equipment, preventing tools and miners from simply drifting away. Human presence on Psyche would be minimal, largely confined to supervisory roles or emergency repairs within shielded habitats. The harsh radiation environment and the extreme vacuum mandate extensive automation. Remote operation centers, potentially located in Earth orbit or on a lunar base, would command the robotic fleet and processing plants. The operational lifespan of equipment on Psyche will be significantly extended compared to terrestrial counterparts. Without atmospheric corrosion or biological degradation, mechanical wear and vacuum becomes the primary concern. Redundant systems and on-site additive manufacturing capabilities will be crucial for maintaining continuous operations and repairing components. Orbital infrastructure around Psyche could include communications relays and refueling depots. These satellites ensure constant contact with Earth and provide staging points for incoming and outgoing cargo. Establishing a stable parking orbit for these assets requires precise station-keeping maneuvers against the asteroid's minimal gravitational influence. The process of extracting valuable platinum group metals is complex. These elements are dispersed within the iron-nickel matrix. Advanced metallurgical techniques, such as leaching with specialized solvents or high-temperature vacuum distillation, will be employed to separate these precious metals efficiently from the bulk material, maximizing yield. Comparing the challenges, terrestrial mining contends with geological instability, environmental regulations, and human labor costs. Asteroid mining, conversely, faces extreme distances, radiation hazards, microgravity environments, and the immense capital investment required for space-qualified machinery. Each context dictates vastly different engineering solutions. Earth's atmosphere and magnetosphere provide natural protection against solar and cosmic radiation. On Psyche, mining operations and personnel will require extensive shielding. Habitats and control centers must be buried beneath regolith or constructed with dense materials to mitigate radiation exposure, a critical factor for long-term viability. The logistics of returning refined materials to Earth are critical. While a significant portion might be used for in-space construction, high-value elements will be transported back. This return journey involves precise trajectory planning and advanced braking maneuvers to safely re-enter Earth's sphere of influence or dock with orbital platforms. The economic model of Psyche mining necessitates overcoming the tyranny of the rocket equation. Launching material from Earth is expensive. Launching from Psyche, with its negligible gravity, is comparatively cheap. However, the initial investment in infrastructure and the long transit times represent substantial upfront costs that demand massive returns. Unlike the finite, politically sensitive resource deposits on Earth, Psyche represents a truly global commons, albeit one accessible only to nations or corporations with advanced spacefaring capabilities. Establishing international protocols for resource ownership and exploitation will be a significant challenge, shaping the future of space economics. The possibility of discovering unexpected elements or crystalline structures on Psyche also exists. The asteroid's unique origin as a protoplanetary core suggests it might harbor materials not commonly found on Earth's crust, presenting new scientific opportunities and potentially even more valuable resources for future industries. The extreme temperature fluctuations in space pose significant challenges for mining equipment. Direct sunlight can superheat exposed surfaces, while shadow causes cryogenic cooling. Materials must be engineered to withstand these rapid thermal cycles without fatigue or structural failure, requiring advanced alloys and passive thermal regulation systems. Maintaining a stable power grid on Psyche, independent of Earth's supply, is crucial. Distributed energy systems, integrating multiple fission reactors and solar arrays, would ensure redundancy. Battery storage systems designed for deep space conditions would buffer power demands, critical for energy-intensive processes like ore refinement or high-thrust maneuvers. Communication delays between Earth and Psyche can range from minutes to over an hour, depending on orbital positions. This latency necessitates highly autonomous robotic systems capable of making immediate decisions without real-time human input. Remote operators will oversee processes, but direct teleoperation is largely impractical for critical, time-sensitive tasks. Potential failure modes for Psyche mining operations include equipment breakdown due to radiation exposure, micrometeoroid damage to critical infrastructure, or navigation errors during material transport. Each failure carries significant financial implications and could delay or even halt the entire venture, requiring robust contingency planning and in situ repair capabilities. The comparison of asteroid mining to terrestrial methods highlights the disparity in resource accessibility. While Earth's resources are finite and often difficult to extract due to geological complexities, Psyche offers vast quantities of valuable metals in a vacuum environment. This eliminates environmental impacts like habitat destruction or water pollution, but introduces new, unique risks. Despite meticulous planning, unforeseen challenges will emerge. The fine metallic dust generated during excavation, for instance, could abrade seals, contaminate optical sensors, or short-circuit electrical systems. Developing dust mitigation strategies, similar to those for lunar operations, will be essential for equipment longevity and mission success. The collapse of a mining operation on Psyche, while unlikely to cause terrestrial environmental disaster, would represent a catastrophic loss of investment and technological expertise. Recovery efforts would be prolonged and incredibly expensive, demonstrating the high-stakes nature of such a pioneering endeavor in deep space. The long-term sustainability of asteroid mining depends on the development of closed-loop systems for life support and resource recycling. For any future human presence, water, oxygen, and waste must be meticulously managed. The goal is to minimize resupply dependence from Earth, transforming asteroid outposts into self-sufficient space habitats. Future innovations will include advanced AI for predictive maintenance and autonomous decision-making on Psyche. These intelligent systems will optimize mining schedules, manage energy distribution, and troubleshoot minor faults without direct human intervention. This integration is crucial for maintaining productivity across light-year communication delays and reducing operational costs. The long-term vision extends beyond mere extraction. Processed metals from Psyche could serve as raw material for in-space manufacturing, building orbital habitats, solar power satellites, and deep space vessels. This off-world economy would drastically reduce the cost and complexity of launching materials from Earth's gravity well, fostering sustained space development. The establishment of a permanent base on Psyche, or an orbital station around it, could transform the asteroid into a strategic outpost. It would act as a refueling point or a staging area for missions further into the outer solar system, leveraging its resources for propellants and construction, ultimately supporting human expansion beyond the inner planets. The advent of asteroid mining would fundamentally alter terrestrial resource economics. An influx of platinum group metals could stabilize markets, while the ability to construct infrastructure in space without Earth-sourced materials would alleviate pressure on finite planetary resources. This shift represents a paradigm change in humanity's approach to scarcity. The philosophical implications of mining an extraterrestrial body are profound. It represents humanity's active transformation of cosmic matter for its own utility, extending its reach and influence far beyond its homeworld. This enterprise compels a re-evaluation of humanity's role as a steward and explorer within the universe. Ethical frameworks for space resource utilization will need to evolve. Questions of ownership, environmental impact on celestial bodies, and the equitable distribution of space-derived wealth will become paramount. Establishing international consensus on these matters is vital to prevent future conflicts and ensure peaceful cosmic development. Ultimately, the endeavor to mine Psyche is not solely about wealth. It is about proving humanity's capacity to thrive beyond Earth, to master extreme environments, and to unlock the vast potential of the cosmos. It represents a critical step towards becoming a truly multi-planetary civilization driven by ingenuity and a relentless pursuit of new horizons. The scientific return from Psyche mining extends beyond raw materials. Studying the asteroid provides unparalleled insights into planetary formation, the processes that shaped early solar systems, and the conditions within protoplanetary cores. Each core sample and geological survey contributes to a deeper understanding of cosmic evolution. The scale of Psyche mining dwarfs any terrestrial equivalent, both in scope and temporal commitment. Missions span decades, requiring sustained international collaboration and multi-generational planning. The success of this endeavor depends not just on technology, but on humanity's collective will to commit to a future beyond its planetary cradle. The silent expanse of space holds vast, undreamt of resources. As humanity gazes upon the metallic gleam of Psyche, the question arises, will the ambition to harness these cosmic riches lead to a new era of interstellar prosperity, or merely amplify terrestrial challenges across a vaster, colder canvas?